In the vast tapestry of human curiosity, few questions resonate as profoundly as those probing the ultimate nature of existence. What is the universe? Could there be more than one? And if so, can modern physics unravel the enigmatic threads of reality or realities woven into the cosmic fabric? The concept of the multiverse challenges our most fundamental assumptions, suggesting that our universe, with its galaxies, stars, and intricate web of life, might be but a single note in an infinite symphony of worlds. Imagine realms where every possible outcome of every event unfolds, where, in some distant cosmos, you already hold the answers to the questions you pose today. This is the multiverse, a hypothesis that stretches the boundaries of imagination and science, inviting us to reconsider the very meaning of everything. Historically, the word universe encapsulated the totality of existence, every star, every galaxy, the entire cosmic expanse, bound by space and time. To speak of multiple universes seems paradoxical, a contradiction in terms. How could there be more than one? Everything. Yet, over the past century, mathematical explorations have unveiled a startling possibility. What we perceive as the complete cosmos may be a mere speck within a grander, more intricate reality. Decades of research, accelerating in recent years with advancements in theoretical physics, suggest that our universe is one of many realms, each rightfully called a universe in its own right. Together, these realms form the multiverse, a concept that redefines reality as a collection of countless cosmic domains, each governed by its own physical laws and histories. The multiverse hypothesis emerges from the interplay of mathematics and observation, a hallmark of scientific progress. Physicist Sean Carroll articulates a critical condition for this idea. Our universe must exist as an isolated island within the multiversal sea to avoid interference from neighboring realms. Without such separation, the gravitational ripples or energetic collisions from other universes could perturb our own, reshaping the cosmic order in ways we cannot yet predict. Yet, this isolation raises deeper questions. The multiverse struggles to explain the origin of the Big Bang, the cataclysmic event that birthed our universe, or why the laws of physics, seemingly fine-tuned by precise mathematical constants, are as they are. These unresolved mysteries fuel skepticism, casting the multiverse as both a tantalizing possibility and a speculative frontier. How, then, can we place trust in a concept describing realms we cannot see, touch, or visit? In some multiverse models, subtle connections between universes might offer experimental windows, faint signals detectable through advanced instruments. However, many versions posit realm system. Apologies for the incomplete response. Let me continue and provide the extended documentary-style rewrite in full, ensuring it is significantly longer, detailed, and immersive, while maintaining the original structure and ideas. Below is the complete, expanded version, crafted to engage and inform as a long-form documentary narrative. In the boundless expanse of human inquiry, where the quest to understand our place in the cosmos drives relentless exploration, few ideas captivate the imagination as profoundly as the multiverse. What is the multiverse? Can the tools of modern physics, mathematics, observation, and reason pierce the veil of reality to reveal not just one universe, but a multitude of realities? Could there exist an infinite array of worlds where every conceivable outcome of every moment plays out, including realms where you, the reader, already possess the answers to the questions you ponder today? The multiverse hypothesis is a radical departure from traditional cosmology, challenging the notion that our universe comprising billions of galaxies, stars, and the delicate spark of life is the sole domain of existence. Instead, it posits a cosmos so vast and intricate that our reality is but a fleeting note in an eternal symphony of worlds, each with its own laws, histories, and possibilities. The term universe has long signified the entirety of existence, the shimmering stars, swirling galaxies, and the vast void of space-time that binds them. To propose multiple universes seems, at first glance, a contradiction, a paradox that defies the very definition of everything. How can there be more than one totality? Yet, decades of rigorous mathematical investigation, gaining momentum in recent years through advances in theoretical physics, have unveiled a startling possibility. What we perceive as the complete cosmos may be a mere fragment of a far grander structure. Our universe, with its familiar laws of gravity, electromagnetism, and quantum mechanics, could be one of countless realms, each deserving the title of universe. Together, these realms form the multiverse, a concept that upends our understanding of reality, suggesting that our cosmic home is but one bubble in an infinite froth of creation. This revolutionary idea draws from a rich tradition of scientific discovery, where mathematics serves as a beacon into the unknown. Physicist Sean Carroll emphasizes a critical condition for the multiverse's plausibility. Our universe must exist as an isolated island within this vast multiversal ocean, shielded from the gravitational ripples or energetic collisions of neighboring realms. Without such isolation, the influence of other universes could disrupt our own, potentially altering the delicate balance of physical laws that govern everything from star formation to the chemistry of life. Yet this isolation raises profound questions. Why did the Big Bang, the cataclysmic event that birthed our universe 13.8 billion years ago, occur at all? Why are the fundamental constants of physics, such as the strength of gravity or the charge of an electron, so precisely tuned to allow stars, planets, and life to emerge? Multiverse models struggle to provide definitive answers, leaving these mysteries as open wounds in the fabric of cosmology, fueling both fascination and skepticism. The challenge of embracing the multiverse lies in its elusiveness. How can we trust a theory describing realms we cannot see, touch, or visit? In some multiverse scenarios, subtle interconnections between universes might manifest as faint signals, perhaps. Gravitational anomalies or unexpected patterns in the cosmic microwave background, CMB, the faint glow from the Big Bang's aftermath. Such signals could, in theory, be detected by advanced instruments, offering a glimpse into these hidden realms. However, many multiverse variants remain beyond direct observation, existing solely in the realm of mathematical prediction. Why, then, pursue such intangible ideas? History provides a compelling answer. Mathematics has long served as a gateway to realities unseen. In 1915, Albert Einstein's equations of general relativity predicted an expanding universe, a notion he initially rejected as implausible. Yet, in 1929, Edwin Hubble's observations of receding galaxies confirmed this expansion, vindicating the math. Similarly, black holes, first implied by Einstein's equations, were doubted until telescopes and gravitational wave detectors revealed their existence. The multiverse hypothesis follows this lineage, with equations leading physicists, including luminaries like Greene, toward a reality where our universe is not singular, but one of many. While empirical confirmation remains elusive, the mathematical elegance of these ideas compels vigorous investigation, echoing centuries of scientific triumphs born from abstract reasoning. At its core, the multiverse concept reimagines reality as a four-dimensional space-time continuum, where every possible event, every choice, every quantum fluctuation manifests in some universe. Popular misconceptions often paint the multiverse as a collection of exact duplicates of ourselves, living out slightly altered lives. This oversimplification misses the nuance. Instead, envision various alternate versions of you, shaped by divergent paths, not mere copies. Quantum mechanics offers a vivid analogy through Stinger's cat, a thought experiment where a feline exists in a superposition of being both alive and dead until observed. In the many worlds interpretation, proposed by physicist Hugh Everett in 1957, no collapse of this superposition occurs. Instead, reality branches into parallel universes, one where the cat lives another where it dies. Extend this to an electron with two possible spins. In one universe, it spins up. In another, down. If this interpretation holds, every quantum event spawns new universes, creating an infinite tapestry where all possible outcomes unfold, each in its own distinct reality. This quantum branching suggests a cosmos teeming with infinite universes, each embodying unique physical circumstances. The implications are staggering. Every decision, every roll of the cosmic dice births a new reality. This idea builds on a historical pattern of cosmic humility. In the 16th century, Copernicus displaced Earth from the center of the cosmos. Galileo and Kepler later showed the sun was not the hub. In the 20th century, Hubble revealed our Milky Way as one of billions of galaxies. Now, we stand on the precipice of another demotion. Our universe may not be the center of reality, but one thread in a multiversal web. This progression from Earth to Sun, galaxy to universe, and now universe to multiverse, reflects a relentless expansion of perspective, driven by the same mathematical reasoning that guides multiverse theories today. Critics of the multiverse hypothesis argue it lacks falsifiability, a cornerstone of scientific rigor. If we cannot test or disprove the existence of other universes, is the idea truly scientific? Defenders counter that testability exists in nuanced forms, perhaps through indirect signatures in cosmic radiation or gravitational effects. Some proponents, like physicist David Deutsch, argue the multiverse is more testable than other speculative theories, such as certain interpretations of string theory. While some envision an infinite array of universes, cosmologist Max Tegmark contends that only those with observable matter and classical spacetime could interact with ours. Universes reduced to abstract quantum wave functions, devoid of tangible structure, would remain undetectable, exerting no influence on our reality. To navigate this complex landscape, theoretical physicist Greene outlines 9 distinct types of multiverses, each rooted in different physical frameworks, offering a taxonomy of cosmic possibilities. The quilted multiverse operates within an infinite universe, where boundless space ensures every possible event recurs infinitely. However, the finite speed of light cloaks these repetitions from our view, rendering them inaccessible. The inflationary multiverse, inspired by Alan Guth's 1980 theory of cosmic inflation, envisions pockets where inflationary fields collapse, birthing new universes with unique properties amid eternal expansion. The brane multiverse, drawn from string theory, posits our universe as a membrane or brane floating in a higher dimensional bulk. Other branes, hosting their own universes, may collide with ours, triggering Big Bang-like events with cataclysmic energy. The cyclic multiverse extends this, suggesting branes collide repeatedly, causing universes to rebound through cycles of destruction and rebirth every few trillion years. The landscape multiverse, rooted in string theory's vast array of possible configurations, proposes that quantum fluctuations carve out pockets with distinct physical laws, each a universe unto itself. The quantum multiverse, aligned with the many worlds interpretation, creates new universes at every quantum divergence, ensuring every outcome is realized. The holographic multiverse, inspired by the holographic principle, suggests that a region's information is encoded on its surface, blurring the boundaries between dimensions. The simulated multiverse imagines realities as complex computer simulations, raising philosophical questions about our own existence. Finally, the ultimate multiverse encompasses every mathematically possible universe under varied physical laws, potentially cycling through infinite sequences of big bangs, big crunches, or big freezes. String theory and its extension, M-theory, demand 10 or 11 space-time dimensions, with the extra dimensions either compactified on microscopic scales or our universe confined to a dynamic D3 brane. This framework allows other branes to host parallel universes, each with its own physics. The implications are profound. Are we merely one slice of a higher dimensional reality? These ideas, while speculative, draw from the same mathematical rigor that predicted black holes and cosmic expansion, suggesting a future where observation might confirm their validity. The multiverse hypothesis is not without controversy. Critics, including physicist Sabine Hossenfelder, argue it risks becoming a theory of everything that explains too much, potentially stifling inquiry by attributing anomalies to other universes. Yet proponents like Greene and Carroll see it as a natural extension of current theories, from quantum mechanics to cosmic inflation. Experimental tests, though challenging, are not impossible. For instance, patterns in the CMB, or unexpected gravitational signatures, could hint at multiversal interactions. Missions like the Planck satellite and future observatories may provide clues, while particle accelerators, like the Large Hadron Collider probe scales, where extra dimensions might manifest. Beyond the science, the multiverse evokes philosophical wonder. If infinite realities exist, what is our significance? Are we unique, or are there countless variants of ourselves living every possible life? The idea resonates with ancient philosophical musings, from Plato's forms to Leibniz's best of all possible worlds, recast in modern mathematical language. It challenges us to rethink free will, destiny, and the nature of existence itself, merging science with existential inquiry. As we stand at this cosmic crossroads, the multiverse remains a frontier of intellect and imagination. It beckons scientists to push the boundaries of observation and theory, seeking answers in the faint echoes of the Big Bang or the subtle ripples of unseen realms. Whether reality is singular or a symphony of infinities, the quest to understand the multiverse drives us to expand the horizons of knowledge, illuminating the vast, mysterious cosmos we call home. Thanks for watching. If this journey into the multiverse and its profound implications has captivated you, show your support by subscribing, ringing the bell, and enabling notifications to never miss videos like this.